Hello and welcome to this mathematical ramblings video on the origins of calculus. In this first part of the series, we're going to be looking at how we can find the gradient of functions which aren't just simple straight lines, whether it's something like a cubic or even trigonometric functions. And we'll look at how first principles can be derived. So firstly, what exactly is the gradient? For a straight line, it's fairly simple. Most people know the gradient of a line is being how steep the line is, but we can go a little bit further mathematically. We write the gradient, at least within calculus, one notation is dy over dx, and that d there stands for either delta, which is the Greek letter which is often used to represent change in, or just difference. So in other words, change in y over change in x. So if we pick 2 points on this line, we'll call them x1, y1, and x2, y2. We can look at the differences in y and the differences in x. If you divide the change in y with the change in x, we're left with y2 minus y1 over x2 minus x1. So for a given straight line, we can work out the gradient of that line to be the change in y divided by the change in x, if you know the 2 points. Then though, you might have also seen the gradient as part of lines in the equation of y equals mx plus c, where m represents the gradient, and I'm just going to show exactly why that's the case. If we take the same what we just showed, we have y2 minus y1 over x2 minus x1. We can substitute y for mx plus c in both y2 and y1, and so we're left with mx2 plus c minus mx1 plus c all over x2 minus x1. This all simplifies down to m lots of x2 minus x1 over x2 minus x1, and that means that m is just the same as dy over dx. So these are just two different ways of writing the gradient, but it's better to write the gradient with dy over dx in the context of calculus because dy over dx is relevant to loads of other functions instead of just being straight lines. Now we can look at what exactly the gradient means in a more applied sense. So for example, if we have a distance time graph like we have here, and we have a straight line on that distance time graph, that implies that the vehicle or the car here is traveling at a constant speed. In any given amount of time, it's going to be traveling exactly the same distance. And to find the speed of the car, all we have to do is pick any 2 points, and we find, as before, the change in y over the change in x. But things get quite a bit more complicated when the graph isn't just a straight line, like here, for example. Not only is the speed of the car changing, but it's also even reversing it sometimes. So what does a gradient mean in the context of a curve? Well, there's no general gradient. There's no one single value of a gradient which is going to apply to the entire curve because the gradient's constantly changing. But what we can do is find the gradient at a particular point, the instantaneous rate of change. So for example here, we want to find the speed of the car, what speed the car is travelling at 3 seconds. What we could do for that is draw a tangent to the curve, and the tangent to the curve is then going to represent the gradient at that point. So if we find the gradient of the tangent, we should have the gradient, the instantaneous rate of change at 3 seconds. The problem with this is that it's difficult to draw a precise tangent, and even if you have a good approximation, it's not really a solid basis mathematically for working out a gradient more generally. If you want to just work out the gradient of a curve without actually drawing the curve, there has to be some sort of way, surely. And there is. We can mathematically draw a tangent and work out its gradient. So that's what we're going to look at. Also, as you can see here, these two lines, they both look like they're quite close to being a tangent to the curve, but obviously they can't both be tangents to the curve. And this just shows how it's very difficult to have a precise tangent to the curve. So how do you do that? Well, it's something called first principles, which I'll illustrate using Desmos. So let's say we have this curve here, and we're trying to work out the gradient at this particular red point. To do that, we're going to have to draw a tangent to the curve, but how exactly do we draw an exact tangent to the curve? Well, let's first think about the properties of a tangent. The first thing is that a tangent, of course, is a line. That will be important later on. And secondly, if a line is tangent to a curve, then it's only intersecting with a curve at one point locally. If it's going through more than once locally, that means that it's not actually a tangent to the curve. And going back to the point about a tangent being a line, you can define a line based off 2 points. So what we could do is we could pick another point on the curve slightly further along and draw a line through those 2 points and see what we get. So let's do that. And we can extend the line as well, and we're left with this line. Is this line tangent to the curve? Definitely not. You can see that it's going through the curve at 2 points locally. That means that it's not tangent. But if we start to reduce the distance between the 2 points like so, you'll see that when the distance is really small, at the moment the distance and the difference between the x values is 0.00001, then you'll see that this tangent is actually, or this line is very close to being tangent to the curve. Why does this work? You might be wondering, well, what's happening is when these 2 points are really close together, as they are at the moment, it's almost as if they're a single point. And going back to what the second property of a tangent, that it only intersects with the curve once, it's almost the case that this line only intersects the curve once. It actually technically goes twice, but it's so close because we have a tiny distance between the 2 points that this is a very good approximation for the tangent, and from this we can then work out the gradient. So using what we just looked at and thinking about applying it more generally, let's say we have the curve y equals f of x. What we're doing is we're trying to work out the gradient of the curve at the point x f of x. So the x coordinate is x, and then the y coordinate is f of x because that's the point on the curve. And then you have a point slightly further along to the right. To be specific, it's h, the value of x is h to the right, and that means the x value will be x plus h, and the y value will be f of x plus h. And then we're going to draw a line through these 2 points, and what happens is, as we reduce the distance between the 2 points, as h approaches 0, then this line is going to become closer to being the tangent to the curve. And obviously, as h approaches 0, then the 2 points are going to be very close to each other. We can then think about actually working out the gradient of this tangent. And the gradient, as you know, of a line, we can use right from the beginning of the video. It's based off the change in y divided by the change in x. So the change in y is going to be f of x plus h minus f of x, and the change in x will be x plus h minus x. So that leaves that f prime of x, all that means it's exactly the same as at the beginning, dy over dx, so it's the change in y over the change in x, the gradient of the function f of x, it's just another notation, is equal to the limit as h goes to 0. The reason we have to use a limit here is because we can't have the distance, which is h, between the 2 points being 0, because if it was, then we'd only be looking at a single point. But because we have to have 2 discrete points, then h can't quite equal to 0. We can get really close to it, but it can't be exactly 0. So we have the limit as h goes to 0 of f of x plus h minus f of x all over x plus h minus x. But we can simplify the denominator because the x this will cancel out just to be over h. And then, as I said, f prime of x is just another notation, another way of writing the gradient of the tangent to the curve y equals f of x at x. And obviously another way of putting this is it's the gradient of the curve at that point, or the derivative of the curve, so the instantaneous gradient at a point. So I hope you enjoyed this video. I'll be releasing another video at some point, just going further with this, the origins of calculus, looking at what exactly the gradient function actually tells you about the original function, so like turning points or points of inflection, and how we can actually apply this limit that we've gotten for the gradient function with first principles to specific functions like polynomials or exponentials, and how we can stop it being a limit, I guess is one way to put it. So please like, comment and subscribe if you enjoyed it, and make sure to hit the notification bell so you're notified of any of my future videos and more content that should be coming soon. Thank you. Bye bye.